So another real common thing that you have to do in these problems is to just determine whether or not precipitation takes place at any level. So this is a does it precipitate question, and there's actually a couple of versions of does it precipitate, but really they both boil down to Q. And because it's for a solubility product, we call it QSP. So remember, Q is the reaction quotient. So if you're asked, does a precipitate form when, or did when these two things, what would you expect to see in the solution, or anything like that? What you're going to end up doing is figuring out what the solubility product reaction quotient is. So QSP is what we call that. So we're going to look at this problem. It says, will barium carbonate precipitate when 1 milliliter of 0.0015 molar barium nitrate is added to 50 milliliters of 0.010 molar sodium carbonate? Now, what you have to get good at doing in these problems is recognizing sort of what you're dealing with when you're looking at concentrations and volumes and of substances. And in this instance, I'm looking at barium from this solution and carbonate from this solution, right? And the reaction I'm concerned about is whether or not BaCO3 solid, this equilibrium, will precipitate from these ions. So we still, even though we're mixing the ions together and it sounds like they're reactants, right? We still write the reaction as a solubility product, that is the stuff dissolving. And then what we're going to do is we're going to calculate Q. Now Q for this reaction, and QSP if you want to put the SP down there for sure, but it's still Q, so I won't hold that against you. Looks like that, right? And so if Q is less than K, then what that means is there's not enough product, and actually it would dissolve if there was barium carbonate solid in the solution. Now you have to understand though, the way this question is phrased, right, is if you put these two ions together, it implies that there's no solid present. So when you mix them together, they'll just stay in solution if Q is less than K. If Q is equal to K, you also see nothing. It'll stay in equilibrium, but technically there won't be any solid. But if Q is greater than K, remember Q is products over reactants, just like any equilibrium constant, right? But if Q, so this is no precipitation. But if Q is greater than K, then precipitate forms. That means there's too much ion in solution and it'll go back to form the solid. And that, again, that's precipitation. So precipitation is the solubility product reaction going in this direction, okay? Well, what do you need to do in this problem, right? Well, you need to calculate the molarity of each ion. So in order to do that, right, molarity of barium ion, it's the moles of barium, which we're going to do millimoles. That's our favorite, right? So 1 milliliter times 0.0015 moles per liter, that'll be 0.0015 millimoles. And that's going to be divided by 500 milliliters. Actually, 501 milliliters. And 0.0, I guess they're sig figs. A lot of times in these problems, the way they're set up is that additional 1 mil really has no effect on the overall concentration, but every time I touch the screen, it wants to go forward. So I'll go ahead and calculate that value, and that's 2.99 times 10 to the minus, let me check here real quick. Oops, sorry. 10 to the minus 6 molar. And then we have to do the same thing, right, for the carbonate ion. So the molarity of carbonate, that's going to be 500 times 0.01, right? So that'll be 50, or 5 millimoles, sorry. And still 501 milliliters. That's 9.98 times 10 to the minus third molar. So now what I can do is I can calculate Q. So I'm going to plug in, I'm not going to rewrite them, but I'm going to plug in my barium ion concentrations. It's this. And my calcium ion or carbonate ion concentration. That goes in here. And I get 3.0 times 10 to the minus 8. So then what I have to do is I have to compare this to this, right? And it ends up being about an order of magnitude bigger. It doesn't matter how much bigger it really is. But what that it tells us is that the barium carbonate, because Q is bigger than K, will precipitate out of the solution. Okay. Again, just to go over what we did, you have to recognize what the solubility product expression is going to be and recognize what the molarities of the separate ions are in the solutions that are contributing. And then what you have to do is you have to calculate what those ion concentrations are given the dilution to the total volume, right? So we work with millimoles of the ion that you added divided by the total volume. And again, the same thing, millimoles of solute added, the carbonate in this case, divided by the total volume. And even at those low concentrations that we have here, you still get a precipitate forming in the solution. So here's another problem. Looks very similar. This is for a manganese carbonate. I don't know why I fixated on carbonates. I think it was just in my head. Anyways, we have 125 milliliters of, 0.75 molar manganese chloride solution. So we got to recognize that we have the manganese ion here that we're using, right? And we're adding it to 135 milliliters of 0.2 molar carbonic acid. And the question is, does it precipitate? And magnesium carbonate, 2+ ion, just like barium, which is why I should have probably used something else, but oh well. This is our equilibrium that we're dealing with. Oh, sorry. Just writing the same thing over. Plus CO3, 2 minus again, my little aqueous. All right, so the first thing we're going to do is we're going to figure out the molarity of the manganese ion, right? So I have 125 milliliters of 0.75 molar manganese. So the millimoles of manganese will be 125 milliliters times 0.75 moles per liter of Mn2+. This is what we're looking at. That's 93.75 millimoles. And then we need to divide by total volume to get molarity. So this is manganese 2+, so molarity Mn2+. That'll be 93.75 millimoles divided by, then my total volume is 135 and 125, so that's 260 milliliters. Yeah, sig figs there. And then that gives me a molarity of 0.3606 molar. All right, so that's part of the problem, but we need the carbonate concentration. And I did this in part to remind you about Ka2 for a polyprotic acid. And Ka2, the concentration of carbonate, is equal to Ka2. So that's equal to 5.6 times 10 to the minus 11, right? Molar. Now, here's the thing. When you dilute it, it doesn't change. So this is kind of a very tricky question. It really sort of gets into your head because you're going to dilute this and you're thinking, well, it should be different, right? But because of the way weak acid ionization takes place, second ionization is almost always equal to Ka2. And as a result, right, you can just use this concentration in the calculation. So I have my Q is going to be equal to 0.3606 molar, right? Well, I get rid of the molarity, sorry, I don't have to put it in there, times this 5.6 times 10 to the minus 11. So that'll end up coming out to, let's see here, 4.2 times 10 to the minus 11. Now, when we look at this Q value, I have a K for the manganese carbonate, right, which is just a smidge smaller, right? But in essence, what this is telling us is a precipitate should form. It might be only a small amount, but it should form.